All right, let's jump right into one of the biggest and you think simplest questions you can ask. What is light, really? Seems straightforward, right? But the answer? Well, it's going to take us on an incredible journey to the very edge of reality and time itself. To get our heads around this, I want you to imagine a single traveler, a single photon. Let's say it was born in the super hot plasma of the early universe, maybe 400,000 years after the Big Bang, right when the first atoms were just starting to form.
So, as the universe finally cooled down enough to become see-through, our little photon started its epic, lonely trip. It zipped right past the cosmic dark ages, it saw the birth and death of the first monster stars, it flew through the swirling formation of entire galaxies, and traveled billions and billions of light years. Until, right this second, it slammed into a telescope we put in orbit around our little planet.
Now, from where we're sitting, that journey took 13.8 billion years. But here's the absolute heart of the mystery we're trying to solve today. From the photon's own point of view, how long did that trip across the entire history of the universe actually take?
The answer is zero. Nothing. Not a microsecond, not a nanosecond. Absolutely zero time passed. For that photon, the moment it was created and the moment it was destroyed happened in the exact same instant. So how on earth is that possible? To figure that out, we have to open the case file on the true identity of light. So how do we solve this? How do we make sense of a timeless traveler? Well, we have to start by looking at the first clues, going back through scientific history, where for centuries the greatest minds on the planet were in a total deadlock about what light even was.
You basically had two heavyweights going at it. In one corner, you had Christiaan Huygens. He was convinced light was a wave, like ripples spreading out in a pond. And that made sense. It explained why light bends when it goes through a prism. But in the other corner, you had the undisputed champion of science, Isaac Newton, and he said no way. He was sure light was made of tiny little particles. He called them corpuscles, like a stream of microscopic bullets. And that made sense too, because light travels in such perfectly straight lines.
For more than 100 years, Newton's particle idea was king, mostly just because, well, he was Newton. But then, in 1801, a guy named Thomas Young came up with the smoking gun for the wave theory. His famous double-slit experiment showed that light creates these interference patterns, which is something only waves can do. And you'd think the final nail in the coffin came from James Clerk Maxwell, who came along and mathematically proved that light is an electromagnetic wave.
So, there you have it. Case closed, right? Light's a wave. But just when science thought they had it all figured out, a brand new piece of evidence showed up that didn't fit the theory at all. It's called the photoelectric effect, and it was a real head-scratcher. So here's the deal. If you shine a light on a piece of metal, sometimes it knocks electrons loose. Now, if light is a wave, a brighter, more intense wave should have more energy, and it should knock those electrons out harder. But that's not what happened. A super bright red light did absolutely nothing. But even a very dim blue light knocked electrons out instantly. It was totally bizarre. It meant that the color of the light was more important than its brightness. The case had gone cold. The evidence made no sense, but then came the plot twist in 1905 from a young, totally unknown patent clerk who was about to turn the world of physics completely upside down. And his name, of course, was Albert Einstein. Einstein came up with this really wild idea. He said, what if Newton was sort of right? What if light energy doesn't come in a smooth, continuous wave, but in these little individual packets? He called them quanta. We call them photons now. And suddenly, everything made sense. A photon of blue light is a high-energy packet. It's like a single cue ball hitting a single electron and knocking it for a loop. A photon of red light is a low-energy packet. It just doesn't have enough oomph to do the job, no matter how many of them you throw at it. So this left physics with a massive headache. You have Young's experiment that proves without a doubt light is a wave, and you have the photoelectric effect that proves without a doubt light is a particle. So, which one is it? You've got solid evidence for two ideas that completely, totally contradict each other. And this is where reality just gets strange. The only possible conclusion, as weird as it sounds, was that both theories were right. Light has this dual identity. It seems to travel through space as a wave, but when it actually hits something, when it interacts with matter, it acts like a particle.
I love this quote from the physicist Sir William Bragg. It just perfectly sums up the bizarre spot scientists were in. They basically had to accept that light was this weird hybrid thing, and what you saw depended entirely on how you looked at it. This idea, wave-particle duality, became one of the cornerstones of this new, very strange world of quantum mechanics.
But, just saying it's both isn't a very satisfying answer, is it? It feels more like admitting that there's something much deeper going on that we don't understand. And to really get to the bottom of this, we have to go another level deeper, into what is maybe the most successful and mind-blowingly accurate theory in all of science.
It's called quantum field theory, and it offers a totally radical view of the universe. It says that the most fundamental stuff out there isn't particles, it's fields. I want you to imagine these invisible, vibrating fields filling every single bit of space. There's an electron field, a quark field, and yep, a light field, which we call the electromagnetic field. This theory is our best shot at describing how reality really works.
So get this, what we think of as a particle, like an electron or a photon, isn't actually a tiny little thing. It's just a concentrated little ripple, a tiny localized vibration in its own field. And this beautiful idea finally brings the wave and the particle together. A particle is a tiny focused wave.
And here's how it all connects. Picture the electron field filling all of space. An electron is just a little ripple in that field. Now, if that electron loses some energy, it's like it reaches out and plucks the electromagnetic field next to it. That pluck creates a new ripple in the light field, and we see that traveling ripple as a particle, a photon. It turns out all the forces of nature are just this, ripples in one field causing ripples in another.
Okay, so armed with this seriously deep, modern understanding of light, let's go all the way back to our original mystery. We now know a photon is a ripple in a field, but how does that solve the case of our timeless traveler?
The final clue is right here, the speed of light. It's the ultimate speed limit of the universe. But the truly weird thing about it, the thing that drove Einstein crazy, is that no matter how fast you're moving, you always measure light traveling at this exact same speed.
This one strange fact led Einstein to his theory of relativity. He asked himself this wonderfully simple question, and trying to answer it forced him to realize that if the speed of light never changes, then something else has to be flexible, and that something else is space and time itself. And this leads to one of the most mind-bending ideas in all of science, time dilation. The faster you move through space, the slower you move through time, at least compared to someone standing still. And if you could somehow, magically, reach the speed of light, time for you would grind to a complete and total stop.
And that's it. That's the final piece of the puzzle. Our photon does travel at the speed of light. So for it, time doesn't just slow down. It stops. Period. From its perspective, that 13.8 billion year journey from the dawn of time to our telescope was an instantaneous event. Its beginning and its end happened at the exact same moment.
So we solved the case, but it leaves us with an even bigger, more profound question to chew on. If light, the very thing that connects us to the universe, experiences no time itself, if it can connect events across billions of years in a single instant, what does that really tell us about the nature of time and our own place in the cosmos?